So ionic compounds are very common. Much of the Earth's crust is formed of minerals, which are ionic compounds. Ionic compounds are present in the foods that we eat. They're present in our bodies. They tend to be very stable compounds because the bonds that hold them together are very strong. Here's some examples. We have Morton's light salt. That's a mixture of sodium chloride and potassium chloride. Tums, the active ingredient, is calcium carbonate. All of these are ionic compounds. This is calcite, a mineral that makes these beautiful crystals. That's CaCO3. And then this one's known as trona, and it's a crystalline form of this mess. But here we see sodium and some other nonmetals, so that's also an ionic compound. You don't need to know those guys, it's just some pictures to show you. So we are going to learn how to write the formulas for ionic compounds. You write the symbol for the metal cation first with its charge. We learn to predict the charges of the group 1A, 2A, and 3A metals because their charge is the same as their group number, right? So you have the symbol for the metal cation with its charge, and then you have the anion symbol with its charge. And if we're talking about a single atom, a monatomic ion, we learned how to predict the charges of the nonmetals, right? You can start at the noble gases and call that column 0 and count backwards, -1, -2, -3. Then you're going to put subscripts on those so that when you push them all together, their charges add up to 0. That's the part that's maybe a little trickier than it sounds. And then you always want to double check. We'll look at it. We're adding the charges. Yeah. So those are the 3 basic steps. So this is a summary of ionic compounds. They always contain positive and negative ions. The first element is usually a metal. Okay, this is really the only exception that you need to know in this class. There is a cation that is composed of nonmetals, ammonium ion, NH4 with a positive charge. So ionic compounds start with a metal or with ammonium. When we write those chemical formulas, all of the charges have to add up to 0. The negative charges have to equal the positive charges. And the formula is going to represent the smallest whole number ratio. It's going to be an empirical formula. Okay, let's practice. So write the formula for the compound formed between potassium and sulfur. Well, first of all, what's the element symbol for potassium? K. And finding potassium on the periodic table, what's the charge that it has? +1. +1 because it's in group 1. And make sure that you're following this because I can stop and explain it some more. This is foundation here and is going to build on this. Sulfur. There's my friend, the train. That's the Amtrak. It's more polite. Sulfur is S, right? And what charge does sulfur have? -2. And we're going to write that as 2 minus, so it doesn't look like an exponent. Okay, everybody with me? If we put 1 potassium and 1 sulfur ion together, would their charges add up to 0? No, they wouldn't. Compounds have to be neutral. Nature really hates it when charges are separated. That's when things like lightning happen, right? So if we push those 2 together, we're not going to get anywhere. So actually, I'm going to move these guys over there. You've probably heard of the crisscross method, and if you know how to use that and it works for you, great. I'd like you to think about this more conceptually than just following a trick. So I'm just going to look at what is my total positive and negative charge. I'm writing all of this out, but you don't have to write it out. When you're making up formulas, you're going to just kind of think about it. So right now I have +1 from the potassium and -2 from the sulfur, and those aren't the same. So I need more positives. So I'm going to write another potassium ion with its charge. So now the total over here is +2. Now the charges are equal. +2 and -2 add up to 0. So I've got enough. I don't want to go any further. So to show that we have 2 potassiums and 1 sulfur, I'm going to write K with a subscript 2 and then S.
So you're saying, like, even if you know the crisscross, we can still do it, but you're saying just to make sure that we're always right, this would be the more ideal.
Yes, you could use this to check your crisscross. The thing about the crisscross method is there are a couple of places where it'll give you a ratio that's like 2 to 2 or 2 to 4 or something, and you'll have to reduce it. And if you think about it this way, that never happens. While we're talking about symbols, it is very important that these symbols be capital letters. Okay? They need to be capital in their shape and in their size. Sometimes it gets a little sketchy when you're just handwriting them. Okay, let's look at aluminum and nitrogen. What's the symbol for aluminum? AL. And that's a capital A and a lowercase l. I make my lowercase l's like that, my capital I's like this, and my 1's are just a line. So that when I look at my writing, I can tell what it was. So this is a capital A and a lowercase l. We can call him Al. A capital A and a capital L is wrong. Making your capital A a big lowercase a is also wrong. That's not a capital A. This is the only place I care about that. If you're writing sentences and you make your capital A at the beginning of the sentence a big lowercase a, I don't care. Here I care. What charge does aluminum have? Well, is it a metal or a non-metal? It's a metal, so it has to be positive.
Oh, so it's plus.
What group is it in?
Oh, 3, sorry.
It's in group 3, so 3 plus. And nitrogen is N, and what charge does nitrogen have? -3. So, we could make lines and add things up, but there's nothing to add. This is +3 and that's -3. It's all good. All we have to do is shove those guys together. And so this is capital A, lowercase l, N.
Okay, so like this, or non-metals, I have to make sure that I'm looking at the group for positives for non-metal, and then anything after that, I'm just counting backwards, right?
Yeah, so the non-metals you're going to count back because they're going to be negative.
Right.
Metals are always going to be positive. And we're going to talk about group 1A, 2A, 3A, and a couple of other guys. Yes?
So for boron, is that
Boron is above
right?
the line. Technically, it's a semi-metal. But if you're doing nomenclature, you'd consider it a non-metal because it's on the non-metal side. Yeah. Any other questions?
Is there a specific name for these compounds?
Mm-hmm. Yep, we'll get to that. Yeah, we'll get to the names. Any questions about the formulas?
Is that going to be today?
Pardon me?
We're going to get to names today?
I think so, yeah. So these guys here, if you crisscross those, you'd end up with Al3N3. And so one of the things you really have to watch out for if you want to use the crisscross method, if these are the same, don't do anything, just shove them together. That'll save you from most of the problems. Okay, naming ionic compounds. So some compounds have common names. Like sodium chloride we call salt or table salt, right? But all compounds have systematic names. And these systematic names seem complicated to students, but they've actually been simplified as far as they can be simplified. We're not trying to make things hard for you here. So to identify the compound type, that's the first step. So ionic compounds, always metal and some nonmetals, unless it starts with NH4, and then it's also an ionic compound. Could you pass the class if you never remembered that NH4 compounds are ionic? Yes, you could. It doesn't come up that much. So these are all examples of ionic compounds. You look at the first element, sodium's a metal, aluminum's a metal, calcium's a metal, magnesium's a metal. Again, we're going to find them on the periodic table to identify whether they're a metal or not. You're not just going to kind of think about it. So ionic compounds can be categorized into two types. The metals that we've talked about in groups 1A, 2A, and 3A always form the same charge as the group number. They're really nice and predictable. And then we've got the transition elements, all those guys in the middle, and they are not predictable. Some of them form like 5 or 6 different charged ions. So those guys are pretty squirrely. So when your book talks about these two different kinds of ionic compounds, that's what they're talking about. This is the first type, is the ones that are predictable, and the second type is not predictable. I don't really like that division, but it's in there, so I've got to kind of deal with it. Okay. So this periodic table is showing us the metals that always have the same charge. And so here we have the metals in group 1 plus 1. The metals in group 2 plus 2. What about beryllium? Well, I'm not going to give you a beryllium compound to name, so don't worry about it. What about hydrogen? Is hydrogen a metal? No. Hydrogen is sitting over there because he's ornery. Okay? He doesn't really belong there. But hydrogen does form a +1 ion. And then we've got aluminum over here in group 3A. So groups 1A, 2A, 3A, and then there's 2 more that you need to know. Zinc and silver. Scandium is there also, but just doesn't come up in this class, so I'm not even going to talk about him. So these charges are predictable from the group number. Even these guys are kind of predictable from the group number. The way I remember these two is, doesn't it look like we're kind of going down the stairs? So this is the third step, and the second step, and the first step. I guess we need to go all the way to the ground.
So aluminum.
3, 2, 1.
Aluminum is the only one in the transition metals that has the.
Well, aluminum is not a transition metal.
No, I mean, like, isn't that the little ladder, the step?
But-
step?
Well, aluminum is, it looks like it could be a semi-metal, right?
okay.
Because it's right next to the line,
Yeah.
but it isn't.
Oh.
Yeah, there's just got to be exceptions to everything, right? Aluminum is a main group element because it's in this section over here. And then these are the 2 transition elements, the 2 transition metals that you do need to remember the charge of. So these are groups 1A, 2A, 3A, zinc, and silver. I'm going to say that over and over and over and over again. The names of these ions are the same as the name of the element. So the name of the potassium well, the name of the ion that potassium forms is potassium ion. The name of the ion that aluminum forms is aluminum ion. We don't need to tell anybody what the charge is because we look at the periodic table and we know. Group 1A, 2A, 3A matches the group number. And then zinc and silver are just going down the stairs, 3, 2, 1. Everybody else, all the other metals, can form more than one ion. Or we're not going to talk about them. So all the other metals that we're going to see in this class can form more than one kind of ion. So here are some examples. So chromium might be +2 or +3. Iron can be +2 or +3. There's a bunch of them here, +2 or +3. Copper, +1 or +2. Tin is 2 and 4. Mercury's weird. They're both +2, but this one is Hg2. It's two atoms of mercury together with a +2 charge. I'd like to be able to just ignore him as well. Lead, 2 and 4. These charges are not predictable because you don't know which of the two you're getting in a given compound, right? So we have to specify which one you're talking about. So this is like calling the house of John Smith, right? And his dad is John Smith Sr., right? And he's John Smith Jr., and then his son is John Smith III, right? And if you ask for John Smith, which one are you going to get? Or King Henry. Well, which King Henry? The first, the second, the third, the fourth, right? There's a whole bunch of them. So when we name these ions, we're going to kind of name them like the kings of England, and we're going to give them Roman numerals after their name to tell us which one they are. So chromium the second, chromium 2 has a +2 charge. Chromium the third, chromium 3 has a +3 charge. Down here, lead the fourth, lead 4 +4 charge. The Roman numeral tells us the charge on the metal ion. Remember, Roman numerals use letters to represent numbers. So that's 1. And if you have 2 I's, that's 2. And 3 I's is 3. And then 5 is V. So this is 5, 3, 2, and 1. I think they realized that, okay, we can't just keep adding I's because that's not going to work. And so 4 is 1 before 5. It's 1 before 5 when you're counting, right? And 6 is 1 after 5. We put the Roman numerals in parentheses just because, but you can make up reasons and say, well, that's to make sure that we don't get confused with letters of the next element or something. These are the older names. They use suffixes us and ik to indicate which one had a higher or lower charge, but it didn't tell you what the actual charge was. So if you run into something with these us and ik things, and here they use the Latin names, plumic and plumus, instead of lead 2 and lead 4, you just go look them up. But those are never going to show up on exams, because that's ancient history. Bad idea. Okay, my tricks. So metal in groups 1A and 2A form ions with a charge equal to the group number. Metals in this triangle are also predictable. Aluminum is +3, and then zinc is +2, and silver is +1. These guys, cadmium, indium, and gallium, also follow in this pattern. Aluminum, gallium, and indium will all be +3. Zinc and cadmium will be +2, and silver's +1. The thing is, we're not going to run into these guys. The ones we're going to see are aluminum, zinc, and silver. So group 1A, 2A, 3A, zinc and silver, do not use a Roman numeral. Because Thomas Kawagoe, there's only one of him in the world, right? He doesn't need a Roman numeral. There's no junior, senior, there's not even a totally unrelated guy, right? He's one of a kind. So we're not going to add stuff onto their names. We want to keep it as simple as possible. So group 1A, 2A, 3A, zinc and silver, no Roman numerals. Everybody else, Roman numeral. Okay, so those are the cations, the anions. So anions are going to be obviously negative, but they're going to be the nonmetals. And so they need a name as well. So the monatomic anions are just, the individual nonmetal elements. And their charges are predictable from the group number -1 or count backward from the nearest noble gas. We covered that. To name the anion, you take the main part of the nonmetals element name, and you change the ending to "ide." So fluorine becomes fluoride. Chlorine, chloride. Oxygen, oxide. Okay? Any questions about those guys? So the metals, we've got groups 1A, 2A, 3A, zinc and silver. Their ion names are the same as their element names. The other metals, there could be more than one, and so it's going to be the element name with the charge as a Roman numeral. The nonmetals, you take the element name and you change the ending to "ide." And you also predict the charge from where it is on the periodic table. So a binary ionic compound has two elements in it. It's going to have a metal and a nonmetal. And so to name the compound, you name the metal, you name the cation first, and then you name the anion. And it's always in that order because that's how they decided to do it. So let's say you're sending out formal wedding invitations. Do you write Mr. and Mrs. or Mrs. and Mr.? Well, today you might want to just avoid those titles altogether, right? But traditionally, it's Mr. and Mrs. Why? It's not patriarchy. I mean, you could get whole into that and get all angry about the past. Everybody just does it the same way. Okay? So I think of the metals as being masculine, like the Mr., and the non-metals as being non-masculine or feminine. So these are like the Mrs.
What about lady and lord?
Well, see, those would be the noble gases, and they don't do this. There we go.
There you go, now we're getting somewhere.
Yeah, and so all of this is just very traditional, right? I grew up a long time ago. So traditionally, a man and a woman get married, and who changes their last name? The woman does. Now, this is no commentary on whether people should do that or anything like this. This is a device to help you remember chemistry, okay? So here's the non-metal. I think of that as the woman. So she's going to change the ending of her name. And that symbolizes that, okay, she's part of a compound. The metal doesn't change his name at all, just like the man doesn't change his name. Why? Because that's how it is, right? So, example, KCl. We've got two elements here. The first one is potassium. Is potassium in groups 1A, 2A, 3A zinc or silver?
Oh, you said one or two, yeah.
One,
sorry.
1A, 2A, 3A zinc or silver. Yes, it is. So no Roman numeral, just potassium, because there's only one of them. So then we have the name of the cation, potassium, and his wifey here is chlorine, and so she changes the ending of her name to ide, chloride, and so potassium chloride. Compound names, element names are not proper nouns. You only capitalize it if it's at the beginning of a sentence. Okay?
When did we go to like height and all that stuff? Is that for?
We'll get to that. Those are polyatomic ions. We're going to keep it simple, just a little bit longer. So, CaO, right? Well, the first element is calcium. Is calcium in group 1A, 2A, 3A zinc or silver? Yes. No Roman numeral, he's just calcium. And then we look at the nonmetal, oxygen, change the ending of the name. Oxide. Now, what if you got confused and said oxygide? Well, people might snicker at you like a bunch of people just did. Would I mark it wrong? Probably not. I would just, correct you. Because some of the names sound funny even when they're correct, so we can't always go with sounding funny as being wrong. Okay, name the compound Ag3N. We always have two ions, right? So what's the first element's name? Silver. Is silver in groups 1A, 2A, 3A zinc or silver? Yeah, it's silver. Silver doesn't need a Roman numeral. And the N, what's the name of that element? It's nitrogen, and we change the ending to nitride. So silver nitride. We're not going to do anything with that 3 because the silver ion has a positive 1 charge. The nitride ion has a negative 3 charge. And so we need 3 of these guys to balance the charge of that one. We don't need to put tri or anything in there. We're going to keep it as simple as possible. We can figure out the formula, the ratio, by using the charges, so we're not going to indicate that in the name. Okay? Write the formula for rubidium sulfide. Now, what's the symbol for rubidium? It's Rb. Ru would be a good guess, but not. Okay, what's the charge on rubidium? Find it on the table. +1. It's over in group 1A. Okay? Sulfide is the element sulfur, so it's a capital S. And what charge does she have? 2 minus. We got the element symbols and the charges, and now we can figure out how many. So I've got a total of -2 and +1. I need more positive ones, right? So I'm going to draw another one in here. We've got +2 and -2. Write it out at first, and then you'll be able to just kind of do it on the whiteboard in your head. So we need 2 rubidiums, Rb2, for every 1 sulfur, Rb2S. Any questions? If we have one of those other metals that needs a Roman numeral, we just stick that in the middle. It's really part of the element, part of the metal's ion name, right? And so the charge in parentheses is attached to the name of the metal, and then there's a space, and then we've got the anion, the nonmetal, behaving the same way. So name this one, CrBr3. Well, Cr stands for chromium. And then you ask yourself, is chromium in group 1A, 2A, 3A zinc or silver? No. It'll need a Roman numeral. Let's not worry about it yet, but we're going to put the parentheses there so we don't forget to come back to that. And then Br is bromide. Bromine is in this relationship combined by the bonds of holy ionic bonds or something, I don't know. Sometimes the analogies go astray. Chromium, bromine, that's not right. Bromide.
So now in this situation, could we cross now? Or no, because.
Well, what we have to do is now we have to go look at the charges on these ions, right? So we're going to kind of deconstruct this guy, and we've got Cr, and we've got Br, and there's 3 of those. Well, what's the charge on the bromide ion? -1. Negative, negative, negative. I'm going to move this. Because I can. So the total there is -3. From that, we figure out what the Roman numeral needs to be, the charge on the other guy. Yeah, it's got to be +3. Because if we have a total of -3, we have to have a total of +3. And in this case, that +3 is all on a single ion. Sometimes it could be 3 there, and then they'd each have +1. So this is chromium 3 bromide. Any questions? Name the compound FeS. Fe is the symbol for iron. Is iron in group 1A, 2A, 3A zinc or silver? No. Okay, Roman numeral. Doesn't matter where he is, it's just that he's not in 1A, 2A, 3A zinc or silver. And then S is sulfide, right? Sulfur becomes sulfide. And we're going to have to figure out what that charge is, so then we have to look at these ions with their charges. We don't know what iron is, but what is sulfur? -2. Remember, we're looking at the periodic table, and we're going to start over at the noble gases. They always have 0 charge. They don't make ions. They don't make compounds. They just don't do anything. They hang around and just ignore everybody else. And so then you count backwards. -1, thank you. -2. Same to you. So, somebody had a bad day. I'm going to make a whole bunch of noise about it. Okay, so here we just have one of each. If this one's -2, that one has to be +2. The total number of positive and negative charges has to be equal, so when you add them all up, it's 0. So this is iron 2, iron the second. So we'll put the Roman numeral 2 in the parentheses. Write the formula for ruthenium 4 oxide. Well, what's the symbol for ruthenium? Are you sure? What's the charge on the ruthenium ion? It gives it to you 4, right? Handed to you almost on a silver platter. So this is 4+. And oxide is what element? O, oxygen. and it's got a -2 charge. So, writing the formula, I need to get the element symbols and the charges of the ions. Then I'm going to look here, and over here I've got +4, and over here I have -2, and those are not equal. I need to fix this by adding more of one. You can't take away. So I need another one of those, right? So that becomes -4, and I have solved my problem. And so this is RuO2. This isn't a compound, but that would be kind of cool. Are you okay?
Couldn't you make it one though? 'Cause I mean, they're all.
I don't think you could actually, because
Oh, it's
potassium's a
unstable?
metal, because you'd have 2 metals.
Oh.
Yeah, I don't think it would work, but you can really play around with stuff like that. Maybe complex on it. Questions?